Bruce Porter, and I had mentioned in the last days in the book of Revelation about impact, which is talking about the effects of an asteroid impact, reading a little bit from Victor Klube and Bill Napier's book, The Cosmic Serpent. So this is a short presentation. When I do this, think of some of the things that are talked about in the book of Revelation, as well as in the Book of Mormon, the events that happened in the Book of Mormon. It mentions 3 times in the book of Revelation that a star or a mountain, twice it says a star fell from heaven. Once it says it were like a mountain that fell from the sky that landed in the water. So you can see these things a little bit. So I wanted to at least give you some type of indication from science, from the science point of view of Victor Klube and Bill Napier, who are astrophysicists at the Royal Naval Observatory in Edinburgh, Scotland. So it's going to talk about the impact and the events of an oceanic impact as well as a land impact. What we see in the seventh seal, when the seventh seal is open, nature is in commotion. And in Revelation chapter 8, verses 7 through 10, it says, "The first angel sounded, and there followed hail and fire mingled with blood, and they were cast upon the earth. And a third part of the trees were burned up, and all the green grass was burned up. The second angel sounded, it was as it were a great mountain, burning with fire was cast into the sea, and a third part of the sea became blood." So a great mountain burning with fire was cast into the sea. That could be, you could consider that an asteroid, not a mountain. And a third part of the creatures which were in the sea had life died, and a third part of the ships were destroyed. Now that would happen because the exposing the mantle, which would be exposed from an asteroid impact in the ocean, the crust is extremely thin there. That would cause, when the salt water and the chemicals in the salt water come back in, that it would create sulfuric acid. And then the third part of the ships that were destroyed would be because of the tsunamis that will be described in Klube and Napier's book that I'll read here shortly, would cause that also. And if you think about it, probably the greatest centers of population are on the coastline. So in verse 9, a third part of the creatures which were in the sea had life died, and a third part of the ships were destroyed. And the third angel sounded, and there fell a great star from heaven, burning as it were a lamp, and it fell upon a third part of the rivers and upon the fountains of water. So we see both of them there. I mentioned before this little quip of the Dr. Moon talking to the sick earth says, "You've got a pretty nasty case of humans. Take 2 asteroids and call me in the morning. Side effects are rather unpleasant, but they only last a few million years, and then you'll be as good as new." And now, how we've come to understand that asteroids have hit the Earth probably more than the moon because of the gravitational pull, as well as the size of the Earth compared to the moon. There's been more asteroid impacts on the Earth than there has on the moons. We have an atmosphere and a climate, weather, in order to erode those, so we don't see them like we see on the moon, but we've had more hit the Earth than there has hit the moon. In Revelation 8, 11 through 13, it says the name of the star was wormwood. That means it's poison. A third part of the waters became poison, wormwood, and many men died of the waters because they were made bitter. And the fourth angel sounded, and a third part of the sun was smitten, a third part of the moon, and a third part of the stars. So a third part of them was darkened, and the day shone not for a third part of it. So this is typical of a land impact, because the ejecta into the atmosphere would cause the almost a total blockage of the sun, and it could be anywhere from a few days to a number of years, depending on the size of the asteroid and whether it was a land impact or oceanic impact or partial land and oceanic impact. This is just a brief map of the largest impact sites that we know. They're pushing 200. They're pushing about 200 craters as of today. They're pushing about 200 crater sites, impact sites in North America. Each of them have a name. Each impact site has a name, and we can see where many of them are. If you notice, most of those are across the northern hemisphere. Now, we would expect, or you should expect, because the ocean covers 70% of the Earth's surface, about 70%, you would have to expect that many of those impact sites are going to be in water, in the ocean, which will cause a lot of damage on the continental shelves without question. But the majority of those are going to be in the ocean, just because of the amount of surface of the Earth that is water. But if you look at it, you'll see that the largest concentration is in the northern hemisphere across the United States, and then in northern Europe. There's a lot of them found in Australia mostly because of the climate there and what's going on there in regard to the erosion with that. This was a printout that was done probably 15 years ago or so. And it's got the continents, it has the continent here on the left-hand side. Russia, Asia, Russia, Africa, North America, South America. It has the continent's percentage of the Earth's land area. So Asia and Russia has 30% of the land's surface area. Africa has 20%. North America only has 16%. South America 12%. Antarctica 9%. Europe 7%. Australia 6%. But then it has the continent's percent of the known craters. Russia has 16% of the known craters. Africa 11% of the known craters. North America 32% of the known craters. South America 6%, Antarctica 0%, Europe 22%, Australia 14%. So the closest thing to North America is Europe, and that's that northern hemisphere. But North America has about 32% of all the known number of craters. Now, when you look at it in numbers, the numbers in North America have now risen from when this was printed, has risen to about 200. Anywhere, some say 160, I've seen 170, I've seen 200 something craters in North America. But if you look at the numbers versus what's happened in North America, there's almost 20% more in North America than the next highest point, or the next highest number of craters for that particular area. So we can see that for some reason North America seems to be a target. Maybe that's because it's the promised land. This particular map is interesting because it shows you the effect of the impact. Tells you about the age. I mean, in this chart you have the time period when they happened, but then it also shows you the impact area, the desolation area of these impacts. The greater the circle, the greater the desolation. So some of them are large, some of them are small. Some of them make a very large impact on life and life stability, or the stability of life within certain regions. And some of these, the one that is thought to have destroyed the dinosaur is the one that is this Chicxulub one off the coast of the Yucatan Peninsula. And it travels many asteroids. There's more than one of them when they travel. There's multiple ones. They may break up in space, but often there's multiple ones. The one that Chicxulub, the one that they think destroyed the dinosaurs, had a companion that landed. I believe it was in Iowa. Is where the Illinois, or I think it was Iowa, where the companion to that one landed. Anyway, these are some pictures of a few of the craters around. You can see there are actually two here on this one. The two companion ones that were traveling. And just like water, when you drop something in water, you have a rebound in the center, and you see part of that rebound that ends up showing up in the center here. And you see that in a lot of these impact sites around that you see around. Here's one. You can see the rebound here in this area of the impact crater. This one you don't see the rebound. This is taken from space. Looking at this is the one in subarctic Canada area up there. This is the Quartzies area impact site right here among sedimentary rocks. So it's not volcanic. They know it's not volcanic. You can always tell what's there. Sometimes the impacts will go below the water level, and so you get water coming back up in the center of these impact sites. There will always be a rim, generally a rim around, because of not just the, it's not a remnant of the asteroid or meteor that hits. It's the surface that is ejected out. Here's one that's created a whole mountain range that surrounds the impact site. Because of the size of what happens. It basically turns the crust into liquid. Here's one that's filled up with water, another impact site. This is one in Arizona. Many people are familiar with its meteor crater. I lived not far from here as a youth and became friends. There was a boy in my same grade. We caught a bus going to school in Winslow. We caught the same bus close to the same bus stop, and so I would sometimes spend the night with him and he with me. But when I would spend the night with him, his dad was in charge of the crater of Meteor Crater, so there was a path. We would go down and get into the bottom of the crater of Meteor Crater here, go right down to the bottom where they had the drilling taking place. I've studied a lot about this impact site because I've actually picked up pieces of meteorite around this crater, living around there and walking around and through there with my friend that lived there. But it's under this north face right here. The south face. It's under the south face. It's flat when you look at it from the top. It goes straight across. The meteor came in from the north and buried itself underneath this area. This is why it's sloughed off, and this is why there's more cliff there, because the meteor is somewhere buried underneath. When it hit, it was coming from the north at about a 30 to 40 degree angle when it impacted the earth and left the crater there. This is it from a distance. This is it from space, looking down on it. This area here, the meteor came from the north, heading south, and it hit, and then it's buried under here. They tried to drill down and tried to find it in the center, but they didn't. Here's some other pictures of other sites. This shows the asteroids, the belts. There's 3 different belts. Well, there's actually 4 different belts of asteroids in our solar system that are circling the sun just like our Earth is. This white area around here, they think that may have been the belief is that may have been a planet at one time. And this is the remains of that planet that's been demolished, exploded, or maybe impacted by something that was larger than it was. Now, asteroids that cross the Earth's orbit, so there's asteroids that actually cross the Earth's orbit, those are called Apollo asteroids. Now, when I was doing the study, they had found about 1,000 of them. Now they're pushing over 2,000 Apollo asteroids that cross the Earth's surface, or across the Earth's orbit around the sun. So we should expect, we see them all the time. We know that they're there, but there's a lot more out there than we would sometimes like to think. Well, the book is called The Cosmic Serpent, written by Victor Klube and Bill Napier. It's a scientific book. They're both, as I mentioned, they were astrophysicists at the Royal Naval Observatory in Edinburgh when they wrote the book. And so I'm going to read some parts of their book. It's not me, but I'll read it. If I interject something, I'll try and let you know that I'm interjecting it. But there's 2 types of impacts that you want to study, and then there's one is oceanic and the other is land impacts. But then the difference of what happens is often dependent upon the size and the composition of the asteroid. The size would be the diameter, generally in kilometers or meters, and the composition would be metal or generally gas or ice, some type of gaseous ice. So as they read on page 76, it turns out that if the current population is typical, an Apollo asteroid, now that's those Earth-crossing asteroids, of at least 1 kilometer in diameter will collide with the Earth every 250,000 years or so. Keeping in mind these are astrophysicists. If such an asteroid has the density of water or ice, its mass is about 4 billion tons, and for the mean impact velocity of 25 kilometers per second, which is normal but not fast. The impact energy is 3 million megatons. For a rocky constitution, the energy will approach 10 million megatons. The unit of energy employed here is the megaton equivalent of TNT, 1 megaton, corresponding to the explosion of 1 million tons of TNT. So understanding that a megaton is 1 megaton, 1 million megatons of TNT. The Hiroshima explosion had an energy of 1/50th of a megaton. Okay. 1/50th of a megaton, not even 1 megaton, 1/50th of a megaton. A sizable hydrogen bond will release 1 to 10 megatons of energy. The Krakatoa eruption of August 1883 was about 50 megatons, and a major earthquake may involve the release of over 100 megatons, but that will be deep down in the earth. So Klube and Napier explain the effect of a large land impact. The comet or asteroid will enter the atmosphere at hypersonic speed, and a shock wave will hug its forward hemisphere and extend backwards as a long cylinder. Essentially, it punches a hole in the atmosphere. The displaced air being thrust sideways from the cylinder at about the same speed of the missile, which could be anywhere from 20 to 50 kilometers per second, creating a blast wave of about 10 million megatons. That's just the blast wave. That's just the force. That's just the air blast wave. The great bulk of the kinetic energy of the asteroid therefore reaches the ground, and the crater develops in a manner already described. Much of the energy is expanded in fragmentation and shifting of the rock, a few percent going into the creation of a high-temperature ball of vapor. The crater of about 200 kilometers in diameter is formed within a few minutes, ejecta being raised through several kilometers and deposited in part in a rim. So it throws material up and then it comes back down in the rim. The atmosphere around the crater will be violently disturbed by these rapid ground motions and by the expansion of the fireball. Further, the passage of ejecta ranging from kilometer-sized lumps to hot ash is expected, and strong interaction will occur between these ejecta and the atmosphere. The proportion of energy ultimately deposited in the atmosphere is difficult to assess with precision. Certainly, in an explosion, a considerable percentage of the original energy ends up as a blast wave. The figure of 10% is adopted below. So it's what's happening as this asteroid punches a hole in the atmosphere. That superheated blast wave that goes out has to come back. It comes back in and fills the hole that the asteroid punches with this superheated material. So, and I don't know whether I'm going to discuss that here or not, but after the impact takes place, then you have this vacuum now of superheated air that is trying to follow that vacuum down that tube, which when it hits the ground, then it disperses across the ground. So that's what you have to be considering that, and that's probably not on this part. Complicated, though the atmosphere disturbances must be in the region of the crater, the situation will have simplified within a few crater diameters, a few minutes after the explosion. Beyond 1,000 kilometers from the epicenter, a shock wave will have formed and be moving rapidly outwards. The situation may be characterized by a cylindrical shock front behind which the atmosphere is piled up into a dense, high-pressure hot shell. The shell snowplows into the as-yet undisturbed atmosphere ahead of it, gathering it up. If, say, 10% of the impact energy is deposited as blast motion into the atmosphere within 500 kilometers of the epicenter, about 400 miles away, then at 2,000 kilometers, a distance wind velocity of 24 kilometers per hour. That's the blast wave, 2,400 kilometers per hour of a characteristic duration of almost a half hour is expected. If there's no back pressure behind the blast, that is, if it's impelled forwards by its own momentum, then at 5,000 kilometers away from the epicenter, the wind velocity has dropped to 400 kilometers per hour, enduring for 0.8 hours. And at 10,000 kilometers from the epicenter, that's 90 degrees away, the wind speed is down to 100 kilometers an hour and will blow at 100 kilometers an hour, will blow for 14 hours. In addition to the dynamic pressure caused by the blast air, there is an instantaneous pressure and temperature rise due to the compression of gas immediately behind the shock front. The shock and blast inevitably deposits energy into the atmosphere, and this appears ultimately as heat. At 2,000 kilometers away from the impact site, the overpressure is 8.5 atmospheres and the air temperature is approximately 480 degrees Celsius. At 5,000 kilometers, the figures are 6 atmospheres and 60 degrees Celsius, dropping to 1 atmosphere and 30 degrees Celsius at 1,000 kilometers away, at 10,000 kilometers. This intense heating expands the atmosphere behind the front, which raises to create a hot, low-density regime. The blast wave thus followed by a partial vacuum, a rarefaction wave of somewhat longer duration. If all the nominal 100 million megatons of energy deposited in the atmosphere were manifested as wind motion, now it's not saying it does, but if it were manifested as wind motion, a mean wind velocity of 1,500 miles an hour would be expected globally. If deposited as heat, then a global rise in air temperature of 43 degrees, that would be Celsius, would be expected. The heat deposition problem is somewhat complicated by the fact that vaporized and melted rock, hot ash, and so on will be flung out of the crater. The vapor and small particles, especially streaming along with the current. This represents an additional source of heat, but the consequences are difficult to assess. About 100,000 cubic kilometers of material is ejected by the impact, much of it in the form of fine dust, which is carried along by the violent motions of the atmosphere. Even in an undisturbed stratosphere, the fine dust quickly spreads globally. The falling speed of a particle, 10 millionths of a centimeter across in the normal, undisturbed atmosphere, is about 1 millimeter per second at 50 kilometers altitude, about 0.1 millimeters per second at 30 kilometers, and about 0.01 millimeters a second at 15 kilometers. At the latter speed, a falling time of 5 years is implied. Very roughly, a particle a tenth as large as has a tenth this falling speed, and the converse. Sub-millimeter sized particles would fall out within about a month. A similar proportion of 100,000 cubic kilometers would result in a blockage of sunlight with an overkill factor of 10,000. Thus, if this simple picture of dust suspension were valid, total blackness would be expected for 2 to 3 years after the impact, followed by a rather sudden clearing of the sky. Now again, the size of the projectile will make, and the makeup of the projectile will make a difference in all of these numbers. A drastic change in the chemistry of the atmosphere, probably of most consequence in the stratosphere, is also likely. Above about 2,000 degrees, nitrogen and oxygen in the atmosphere combine to give nitric oxide. Each megaton injected into the atmosphere will produce between 1,000 and 5,000 tons of nitric oxide, and this will be carried into the stratosphere. An injection of 100 million megatons therefore implies the creation of several 100,000 million tons of nitric oxide between 15 and 40 kilometers altitude. Ozone filters out biologically damaged ultraviolet solar radiation. The mass of ozone in the atmosphere is comparable with the ejected mass of nitric oxide. The latter, however, destroys ozone by a catalytic reaction in which 1 gram of NO removes 100 to 200 grams of ozone. The result of the impact would therefore be a complete removal of the ozone. While this hardly matters when sunlight is blocked by dust, in any case, the question would become important if by the time the dust clears, the ozone was still depleted. The time scale for the replenishment of the ozone is 20 to 30 years. Apart from these atmospheric effects, mention should also be made of a ground effect which may be of consequence well beyond the crater. The energy carried by the shock penetrating the ground shatters and heats the rock, expelling some of it into the form of the crater, but a small residue of this energy will spread beyond the rock, fragmenting the region. Once the tensile strength of the rock is greater than the shock pressure, the rock no longer fragments and the energy is transported by vibration. Probably 1% or so of the total energy is thus carried away by seismic waves. For the impact being discussed, about 10 million megatons will go into these vibrations, much of it as surface waves or earthquakes. The Raleigh or corkscrew and Love to and fro waves, which comprise earthquake motions, damp slowly with the distance. The amplitude of 5,000 kilometers is still being a third of that near the epicenter, and at 90 degrees from the impact point of the energy, kilometers squared in the ground motions will still exceed 10% of that around the crater. A mean global value of about 0.01 megatons kilometers squared is implied. This is at the extreme top end of the earthquake intensity scales and corresponds to a great catastrophe, with, for example, earth layers being overturned, clefts appearing in the ground, and freestanding objects and creatures being thrown into the air. So it would be a massive earthquake. Again, all of this stuff is the way Kluge and Napier explained these things is very close to what we see being described within Scripture. To sum up, the immediate global effects are violent, scorching wind, the ejection of incandescent material, severe earthquake, possible or prolonged obscuration of sunlight, and exposure to ultraviolet radiation of germicidal intensity when the sky clears. That's a quote from Kluge and Napier. This, not long ago, a few years ago, not a long time ago, there were asteroids that were heading towards Jupiter. And it shows them in Jupiter. It has the impact down on the bottom that shows the impact site, and then a day and a half after, so they can see the blast wave going. And then 3 days after, then the second impact, you have there were 9. It's called the Shoemaker-Levy 9, and then you have 5 days after, and the destruction that takes place. This was not that long ago. It's called the Shoemaker-Levy comets. And this is the picture on the left here, the red. This was the picture of the impact. This is the telescopic picture of the impact when it hit. These are the comets that were going through. They saw the comets coming down below, but this is what happened when it hit. You can see the fireball. You can see the energy that's being expended on the lower part of Jupiter there. And this is Gene Shoemaker here. I've met with him before. I've talked to him in his office. I've gone to his office and talked to him about impact sites and craters and things. He was actually scheduled to go to the moon, but he had some health problems that kept him from doing that. But he has probably done more work and research about about asteroid impacts than just about anybody else. I was able to share some research that I had discovered too. There's an old Egyptian story, and this is what he wanted from me. Some of the things that he wanted from me is there's an Egyptian story that's an ancient Egyptian that comes from almost the time of Moses or before, that a dinosaur, it's called the story of the shipwrecked sailor. And a man is shipwrecked on an island, and there's a dinosaur there, and the man asks the dinosaur picks him up and takes him to a cave where it can look at him eye to eye, and he asks the dinosaur why he's there, and he says, while he was away from home, a star fell and hit the earth and killed all of his people, and only he was left alive to tell about the star. The star coming and killing all his family. So it was kind of interesting and an ancient story that connected the work that Gene Shoemaker was doing here. And this is what we could see of the impact sites on Jupiter. Well, anyway, that is what's going on there. Now, the oceanic impact. Experiments on crater formation. This is Kluge and Napier speaking. The experiments on crater formation in sand show that the size of the crater in loosely bound material may be up to 10 times those of corresponding craters formed in rock. A very large, shallow crater, perhaps 500 to 1,000 kilometers across, would be formed by the impact of a 10-kilometer diameter asteroid. So now they're using a 10-kilometer. Now it doesn't have to be that big, but the crater walls being formed of water rather than earth. The whole structure, because of the great dimensions, would take over an hour to form. Of course, the oceans whose depth would be less than the diameter of the asteroid is quite unable to absorb the impact momentum, and a true crater will be formed in the seabed. It has to hit the crust, breaking the crust and exposing the underlying hot mantle material. The shattering of the ocean bed material will not be greatly affected by the overlying water, but its evacuation will be. In effect, some of the ballistic energy of excavation will be transferred into water wave motion. Lifting and displacement of the underlying rock may be a prime input in the oceanic disturbance. The filling in of the water crater will create a rebounding column of water mixed with solids, the whole reaching several kilometers in height. Because in the latter stages, the inrushing water is flowing over lava, some energy transfer is expected. It might be considered that a square centimeter column of water, several kilometers deep, will not be significantly affected by heating through contact with lava at one end. However, the possibility exists that some of the heat energy is expended in overturning the lava, in which case a rapid convective mixing of the lava is possible. The heating then becomes a volume rather than surface phenomenon and may be quite significant. The energy contained in a 100-meter depth of lava, a 2,000 degrees Celsius, in a crater of radius 100 kilometers is about equal to the initial impact energy, and this must complicate the subsequent flow of the displaced water. But we're going to neglect the effect here, they say. The crater expert Gault and his colleagues carried out a calculation in which 1.4 kilometer diameter asteroid struck the ocean at 25 kilometers per second. They found that 92% of the impact energy went into splash, shock heating, and wave formation. The ocean was evacuated to a depth of 6 kilometers over a radial dimension of 15 kilometers. Neglecting turbulent dissipation of the wave energy, they found that the ripple spreading outwards had an amplitude of 1 kilometer at 100 kilometers distance from the epicenter. So your wave is a kilometer high at 100 kilometers from the epicenter, dropping off in proportion to distance, so that, for example, the wave amplitude was 50 meters at a distance of 1,000 kilometers. Approaching a shoreline, a wave slows down and increases in amplitude, in height, as it enters shallow water. There's a piling up of water as the forward part of the wave slows down, an increase in wave height by a factor of 10 as the coastline is reached is expected, so that the 50-meter wave would become a half a kilometer in height if it was a 50-meter wave in the depth of the ocean. The important question, however, is the stability of the impact-generated waves. Development of the wave structure is a complicated technical problem, and work carried out by Asteroid suggests that the waves may break up and dissipate in the ocean. The reason is that the waves are steep, not sinusoidal. Piling onto each other, they evolve into a hydraulic bore, an almost vertical wall of water in an extreme case which cannot maintain its shape and therefore breaks up in the open sea. So the weight of the water can't contain its height and will begin to break up. However, they go on. The steepness of the waves, in turn, comes from the small dimension over which the energy has been deposited. Thus, in the Gault calculation, one has energy greater than that of any earthquake-induced tsunami dumped into a mere 200 kilometers square of ocean. A normal tsunami may be introduced by a sub-oceanic earthquake covering an area of 30,000 square kilometers. The waves generated are of great length and are very shallow. On a ship at sea, one would scarcely notice the swell. These long wavelengths tend not to be destroyed by passage into shallow water and can therefore deposit their energy right on a coastline with devastating effects. The situation may be quite different with an asteroid of 10-kilometer diameter, for in that case, the collision energy is 1,000 times as great as the submarine crater has an area comparable to that covered by the large earthquake. Thus, the ground motions, which will couple into the overlying water, will generate waves of lengths comparable to that generated by a normal earthquake. Of course, the energy transported implies a much greater wave amplitude of 1,000 kilometers from the epicenter. The wave would be on the order, the deep ocean wave would be on the order of a half a kilometer in height. For a wavelength, say, of 100 kilometers, this still represents quite a shallow wave. Pending detailed calculations or observations in the field, it seems likely that this wave energy can be transported over global distance, at least until it reaches a continental shelf or a coastline or shallow sea, where it will rear up and transform into a breaker kilometers high. A run-up on land would create a hydraulic bore of awesome dimensions and a deep and catastrophic inundation of the land. So that's kind of what we see with the oceanic impact, according to the astrophysicists Bill Napier and Victor Klube. The book is worth reading if you're into math. There's a lot of math in it, a lot of science in it. So, but the things that they describe, and again, the size and the makeup of the projectile makes a big difference in the effects of the impact. But the things that are described in the book of Revelation and in 3rd Nephi are the same things that they describe within their book, the Cosmic Serpent. And the book of Revelation mentions three different impacts that may have been, I mean, they could be traveling together, they could be separate ones or different ones, but it mentions three different impacts. One is a mountain, and two as stars that fall to the earth and cause a lot of the destruction and a lot of the earthquakes that take place. So, again, man can survive. It just depends on how large it is and where they live compared to where the impact site is. But it's a lot of fun. It's a lot of fun to look at if you want to spend some time doing it. I've been collecting material on this since the 1980s, since Lewis and Walter Alvarez introduced the theory that the asteroid may have caused the destruction of the dinosaurs. An asteroid, a metal asteroid, has iridium in it. Iridium is a heavy metal, and over all of the dinosaur bones that they excavate, they find approximately a centimeter of iridium dust. The iridium dust on the Earth is so heavy that it's towards the center of the Earth, but with an asteroid impact, that ejecta that goes into the atmosphere would come back after blockage of the sun, would fall back to the Earth, and the dinosaurs the dinosaur bones that they discovered have about a centimeter of this iridium dust over the top of all the bones. And so their conclusion, Lewis and Walter Alvarez, their conclusion was that the demise of the dinosaurs may have been because of the asteroid impact. And there's multiple things that could happen, not just the burning, not just being there. It could happen instantly. It could be the ejecta. It could be the blockage of the sun, entering into another ice age. It could be any number of things that could happen in that. So anyway, it's a lot of fun. Spend some time looking at it if you want. If not, don't worry about it. And really, nobody has to believe a word I say. That's the rule of my class and anything I say.